Hello everybody, this video is about multiple linear regression with scikit learn in Jupyter Notebook. So let us load the data. To load the data we need to import pandas library, the first thing to do. So import pandas as PD. Then we read the data. Okay, let me annotate. First thing is importing pandas library. Then reading the data. To read the data, I take the object my data as the variable. So my data dot read CSV parenthesis the code, and then the data is found in this folder. This data lake data here. So I copy the directory, I bring it here, I paste it, then I double the backslash dot CSV. I double all the backslashes, or I change them into either one. You want to change them into slash, it's also fine. And we run it. So the data is already read. Let's explore the data a little bit. Data dot describe. So this is the content of the data. You have ET as evapotranspiration, SH as specific humidity, AT as air temperature, ST as soil temperature, P as precipitation, SM as soil moisture, and the lake level. So this is the first six variables are the input variables or predictors, and the lake level is our target variable or response variable. So we are going on to provide the input and output data. Otherwise known as predictors and regressors and predictor respectively. So the predictors, the X must be a two-dimensional array with at least two columns in our case here, because it's multiple linear regression. So two-dimensional array with at least two columns. Whereas the output variable, which is y or lake level in our case here, can be just one-dimensional array, because we are dealing with multiple linear regression. So this is the reason why we have the regressors as 2D array with at least two columns, while the regressor y is generally 1D. Okay, so the input data, which is X, our regressors, X equal np dot array. Have my data. It's like slicing for the first brackets. In the second bracket, because you have multiple linear regression, we are going to have a list of these variables, starting with our first, which is et, and then sh to sm. So second is sh. Then let me take 80, then p, then sm. Okay, the reason why I dropped the st, which is soil temperature, is let's go to see the correlation coefficients between them. Oh, we have a crop with double R instead of one R. Okay, this is the correlation coefficient between all the variables, and we are going to see between st and 80. So you see 0.85, they are really highly correlated, so we cannot take both of them as predictors because it's going to cause what we call the multicollinearity, so you have to drop one of them. And I decided to drop the soil temperature because you know that the radiation generally come from the sun and hit the air, then hit the soil. So basically the temperature in the soils depends on the temperature in the air, which also depends on the sun radiation. So based on my intuitions, I decided to drop st instead of 80 because st is dependent on 80. Okay, so this is our input variables. So we have 5 instead of the 6 from the beginning. So let's see the shape. You have 240 rows and 5 columns, so 240 observations and 5 columns, which is the variables from et to sm, excluding st this time. And let's see, let's print XMC. So these are the respective columns. This is for evapotranspiration, this is for specific humidity, this is for air temperature, this is for the precipitation, and this is for soil moisture. This is the list of these 5 variables. So now we are going to input to provide the output variable. This is our y, our predictor, our response variable. Okay, so y equal np, is still an array. My data this time is lake level. Let's see y dot shape. We have 240 observation and just a column, which is the one of lake level. Let's print y and see. This is what you got. Okay, now the next step is the model itself. we are going to create the model. The first thing is to instantiate, so instantiation. Using linear regression class. So model equal linear regression parenthesis. Then we are going to fit the model. Using dot fit. So let's say my model this time equal model dot fit x comma y. We can do both at the same time, instantiate and fit the model. Instantiation and fitting the model. Just in one line of code, we combine all this together. So we are going to say my model equal linear regression parenthesis dot fit x comma y. The same thing, we just combine these two. We take this, the first line of code, we put this here, dot fit xy with this. It's the same thing, but I put them differently just for understanding purposes. So the model is already instantiated in a fit. So the next thing to do is to output the results of the regression. So outputting the results, the regression results. Okay, for this purpose we need to import scalar.matrix. So import scalar.matrix. Okay. Then we are going to print the coefficient of determination. Or what you call R square. So R square equal, my model dot score x comma y. So this is going to give us our R square. Then we are going to print it. Print the coefficient of determination is colon within the quotes comma R underscore SQ. This is this object here. So when we run it, it tells us here that the model, including these 5 variables, explain about 34.54% of the lake level variability. Okay, otherwise the lake level variability is explained at about 34.54% by evapotranspiration, specific humidity, air temperature, precipitation, and soil moisture. Okay, now we are going to print the intercept or the bias. Okay, print parentheses quote the intercept is column comma my model dot intercept underscore. The intercept, we have this what we call beta 0 also, or bias. So what you get here, 282.09. okay, it means that with no impact of evapotranspiration, soil, specific humidity, air temperature, precipitation, and soil moisture, the lake level is about 282.10 meters. So when there is no influence of these 5 input variables, this is what we get as lake level, 282.10 meters. So now we are going to print the slopes or the coefficients of each of these variables. Of the input variables. Basically it's beta 1, to beta 5. Print parenthesis quotes. So the slopes are colon, so the parenthesis comma my model dot my model dot coef and underscore. So the intercept underscore here holds the bias, and the coefs underscore here holds the slopes. Okay, so these are the respective values of beta 1. Here we have beta 2, beta 3, beta 4, and beta 5. These are the coefficients of evapotranspiration, specific humidity, air temperature, precipitation, and the soil moisture. Okay. What it means here that I'm going to include the units of these variables. For instance, here the unit of evapotranspiration is kilogram per square meter per second. It means that the increase of evapotranspiration by 1 kilogram per square meter per second leads to a decrease of lake level by 1.85 10 to the power 4 meter. That's what it means. So when we see an increase of evapotranspiration by 1 kilogram per meter per second, the lake level decreases by 1.84 10 to the power times 10 to the power 4. Here is for the specific humidity. It means that the increase of specific humidity by 1 kilogram per kilogram, this is the unit of the specific humidity in my case here. So the specific humidity is kilogram per kilogram. So kilogram per kilogram of humidity per kilogram of air. So when the specific humidity increases by 1 kilogram per kilogram, the lake level also increases by 6.05 meter. And here is for temperature. The unit of temperature is Celsius degree. So when the air temperature increases by 1 Celsius degree, the lake level decreases by 6.57 10 to the power minus 2. So the increase of air temperature leads to the decrease of lake level, as well as the increase of evapotranspiration, and these are the values. While the increase of specific humidity leads to the increase of lake level. Here is for the precipitation. So the unit of precipitation in our case here is millimeter. So when the precipitation increases by 1 millimeter, the lake level decreases by 5.51 times 10 to the power minus 4 meter. This is confusing a little bit because we expect the lake level to increase by the increase of precipitation, but this is not the case. It means that there is no direct relationship between precipitation and soil moisture. And if we check the correlation coefficient, which does not mean necessarily causation, we can also see already that something is a little bit wrong there. So either clearly there is no direct relationships, or we can see that there is a time delay between the response of lake level to the input of precipitation. So for the last one is soil moisture, and the unit of soil moisture is kilogram per square meter. So when the rise of soil moisture by 1 kilogram per square meter increases lake level by 7.16 times 10 to the power minus 3. It makes sense. So the more we have moisture in the soil, the more lake level will increase. Okay, so this is basically the explanation behind these coefficients here related to our output variable, which is lake level. Excuse me. Sorry. So now we are going to go to the next step and make prediction. Right. Equal my data, my model, dot predict. We are going to predict x, but make sure that in your case, when it's practical, you have to divide the data into train and the set and the test data set. I'm not doing this. so I just went directly to make prediction. But in a very practical way, you need to train the model and then test the model. So the prediction should be made on the test data or validation. So now let's run first. So printing the predicted values is the next step. Sorry. Print parentheses the predicted values of lake level are from comma ypad comma set equal quote \n. This is what we get for the 284 observations, because I took the whole data set. So these are the predicted values. Another way of getting the predicted values another method, let's see, ypad equal my model. We are going to use the equation my model dot intercept plus np dot sum of my model dot waves underscore multiply by x axis equal 1. Okay, this is we know that the predicted value equal intercept plus, let's take the case of sample linear regression. So you have intercept plus beta 1 multiply by x. So this means here. So the intercept, this is for the simple linear regression. I repeat again. We have for the simple linear regression the ypad equal the intercept plus the beta 1 times x. Okay, but since you have multiple linear regression, you have several x's. In our case here, we have 5 x's. So we take the array and we sum all the model coefficients beta 1 to beta 5 times x1 and so on. So the sum of beta 1 times x1 plus beta 1 times x2 plus beta and so on to beta 5 times x5. That's what it means here. So then we are going to write again, we are going to print it, print same thing, the predicted lake level values. I abbreviated lake levels. Values are column, comma, white pad, comma, set equal quote \n. So I said again, as I said it, the predicted LL for lake level. So values are this. So it's the same thing. If you compare them, the values are the same, but the way to compute them are different. The way is 281.72 for the first, and the last is 281.34, 9 something. So 281.72, 26008. This is the first. And we compare the last one to the last, which is 281.849. This here. So, okay, now we are going to compute the coefficient of determination on the predicted value. R square for the prediction. For this, we need to import from scalar.matrix import the class R2 underscore score, this method. Then after importing R2 square from scalar matrix, we type this code: R score equal R2 underscore score y print. Normally it should be on y test. If we split the data into train and test, should be on y test. We run, and then we are going to print our R square. The coefs of determination. And the prediction is column, comma, R underscore SQ, R square. Okay, there is no change, almost no change at all. So it's still 34.54. The next step to do is the model evaluation. For this, we need to import this class importing matrix class from sklearn import matrix. Excuse me. The mean square error the mean absolute error source first. Print the mean absolute error MAE is comma matrix dot mean underscore absolute error. Why quit? Run it. Okay, matrix. Okay, matrix. Oh. Sorry about that. Okay, this is the value of the mean absolute error. Now we are going to have the mean square error. Or MSC. Print the MSC is matrix dot mean squared error y right. Okay, the last thing, if you would like to determine the absolute the root mean square error, or RMSC. So print the RMSC is this time we need an array np dot square root square t matrix dot min squared error right. Okay, and if we would like to plot the predicted against the observed back level, so here again we have to import some libraries and classes. We need from sklearn import linear model, and from scikit dot model selection import cross val predict. Then we need the matplot, lib matplot lib dot pyplot as plt. Sorry, I think these three we need them. From scikit import linear model, from scikit dot model selection import cross val predict, import matplot lib dot pyplot as plt. Okay, the next thing to do is to set the figure. Boundaries, pick, comma, ax equal plt dot subplot parentheses ax dot scatter pret then ix dot plot y dot min y dot max again for the boundary, the upper lower y dot min comma y dot max. Okay, figure boundaries and characteristics. Okay. Okay. Which we call for we need to close the parentheses here. Rather. Okay. Now is labeling. X dot set underscore X label. Our X label is the observe late label. The unit is in meter. Ax dot set Y label. The Y label is the predicted late label. The unit is in meter as well. Then you have the plt.show function to show our plots. So let's run the code and see. Okay, let's see what is the mistake. Y.max instead of ymax here. What is the other mistake? Maybe this is the one. Okay. Okay, this is our plot of the predicted against the observed against the predicted late level. So x against y. You see here the line of best fit, and you see the distribution of data. You can understand why the model is playing about 34.54%. The variance is a little bit high here. So I hope this video will help you in your work. Thank you for watching. Have a happy New Year 2021. Thanks.